So in regard to that, first we need to understand what is biosensing device. So a particular biosensor has got so many parts. First part is we need human samples. So basically saliva, urine, or plasma, or serum. And sometimes in laboratory, we actually use the buffer for testing purposes as well. So these are all human samples which we actually use as the analyte. And then there comes molecular recognition element. This is basically antibody molecules or aptamer molecules, which are basically the binding agent between active area of the sensor surface as well as the target detection molecule which we actually want to detect. And there comes the electrical biosensors. So there are different type of biosensors available these days. So mainly I'll be talking about electrical biosensors, and there would be a signal generator which actually detects the biological interpretation in terms of electrical signals. And there would be readout element which would depict the graphs or results which actually happen in the sensing surface. So here mainly I'll be discussing two type of biosensing devices. First one is FET based biosensor based on zinc oxide, and another one would be zinc oxide and graphene based heterostructure based electrochemical biosensor for direct electron and molecule capture. So mainly idea is that first here the material which I have used for my research purposes was zinc oxide. Now in order to capture biomolecules we need a platform. So the platform was developed with zinc oxide nanorods. To grow those nanorods in an aligned way, in a proper way, we first need to get a good seed layer, because without the seed layer, the zinc oxide nanorods wouldn't be that much directional and optimized length. So first, the optimization for growing the seed layer has been done. Next, the rational zinc oxide nanorod geometry optimization has been carried out to lower down the molecular detection limit and enhance the SNR ratio. After that, we tried to research on vertical electrode configuration for the direct capture of biomolecules on the sensing surfaces. And lastly, we'll be discussing on electric field mediated point of care biosensing devices on flexible platform, which would be used for direct capture of biomolecules. Now, first I'll be discussing about influence of surface defect states on FET-based biosensing attributes in zinc oxide-based thin film transistors. Now we are all familiar with the zinc oxide atoms. So here hexagonal close packed atom, all the tetrahedral sites, half of the tetrahedral sites are occupied with zinc atoms, and all the octahedral sites are quite empty. So that actually promotes so much defects which are ionic defects like zinc interstitials, oxygen vacancies in the atoms. So if we cannot control these particular defect states, it can hamper our mobilities, it can hamper on-off ratio as well as transconductance of the device. So in order to tackle this type of defect states, we have to first analyze what would be the surface roughness parameter and what would be its variation in terms of our zinc oxide thin film growth. So that particular study has been done over here. What we can actually saw here is that with increasing surface roughness, the transconductance actually lowers, transconductance actually degrades. However, with the increasing surface roughness, the active area which is actually available for antibody antigen binding does not actually increases, rather it actually reduces. This is due to the fact that peak pitch, which is the peak between which is the difference between two peaks, that particular thing is actually getting reduced. So the antibody and ion molecules cannot mimic the surface asperities which are present properly due to steric hindrance effect. So the active area which are available for the antibody antigen binding density is actually getting reduced. This particular thing has been realized using zinc oxide thin film deposition by electron beam deposition technique. Here we have varied two parameters. First one was the current which actually we have used. That particular parameter has been varied. And apart from that, the deposition time, which is the primary parameter which has been varied here, is been varied around 90 seconds to 120 seconds to 140 seconds to 170 seconds. So there were four batches of sensors which actually we realized. So if we can consider the characterization techniques over here, we get to see that the PL spectra actually shows two main spectrum. One is for NB, that is near band edge emission. This is due to the near band excitonic recombination in the zinc oxide. And there would be DLE, that is deep lemmal emission. Deep lemmal emission is this peak actually happens due to the presence of oxygen vacancies. So the NB versus DLE ratio actually gets degraded as we move on from TFT1 to TFT4. Now TFT1 represent the batches of sensors which has got 90 seconds of deposition time, and TFT4 actually depicts those batches which has got 170 seconds of deposition times. So deposition time has been varied from 90 to 170 seconds from TFT1 to TFT4. So, if we consider the XRD spectra, we get to see that the 002 axis growth, which is the C axis growth, which is very prominent in case of zinc oxide, the intensity of the peak is decreased as we move from TFT1 to TFT4. However, something different happened when we consider antibody binding density. TFT4 has the better performance in terms of available area, in terms of antibody and antigen binding densities. And in case of Raman spectra also, A1 longitudinal optical mode, which is present in the Raman spectra, it actually the intensity actually increases as we move from TFT1 to TFT4, because this particular A1 ELO mode comes from the oxygen vacancy. And we have also studied AFM characteristics as well. Here we can see that the surface roughness actually varied from 7.2 nanometer to 30 nanometer as we move from TFT1 to TFT4. So all these characterization actually suggest that as we move from TFT1 to TFT4, as we increase the deposition time, our surface roughness is actually enhancing, our defect density is actually enhancing as we move from TFT1 to TFT4. Now, this type of study can be done in terms of realization of these devices like transfer characteristics, IDVGS characteristics. The main fundamental finding using these graphs was on-off ratio actually changed from 10 to the power 3 to 5 as we move from TFT1 to TFT4, which actually suggests that as we increase the surface roughness, grain boundary densities actually gets increased. As we increase the grain boundary densities, so there would be so much electron scattering centers and there would be so much trapped states would be present. So that would degrade the mobility. Now we have also studied the reliability of this particular biosensor. What we get to see is that till 15 days of time, if we preserve our sensing devices, it can actually provide good sensitivity, which was actually present beforehand. Sorry for the background noise. Anyway, the inference drawn from this study was we get to see that detection limit was 0.06 femtomolar for PSA biomolecule detection, and surface roughness increases beyond a certain limit if the effective area available for antibody capture does not increase like that. It actually reduces. And antibody binding density has got a non-monotonic behavior, and we tried to optimize the defect states over here. So major problem was zinc oxide thin films continuity. It was an issue. So in order to tackle that, we actually considered electron beam deposition technique for that. And there were one another problem which we faced, which was Raman spectroscopy was very impossible thing on glass substrate. To carry out this particular difficulty, we actually used smoothing technique, which is Savitzky-Golay. Next, I'll be talking about geometry optical optimization of zinc oxide nanorods for improved sensing performance of the FET biosensor. So far we have tried to optimize the zinc oxide seed layer. Now, on top of this seed layer, we need to optimize zinc oxide nanorod growth. Now, in this particular study, we actually considered silicon nanowire transduction mechanism, and we tried to incorporate that particular. There was a paper from Purdue University. We tried to understand that particular paper, and we actually took their transduction mechanism and incorporated that in zinc oxide nanorods. And we have also considered one parameter, which is liquid penetration depth. Now, what is a liquid penetration depth? When we provide liquid in nanorod surfaces, the consecutive two nanorods have got spacing. That particular spacing does not penetrate with the buffer solution or serum solution completely. So the particular length that is actually getting penetrated, that is considered to be liquid penetration depth, which we tried to model over here using computational fluid dynamics method. So we tried to establish empirical relationship with the nanorod spacing, which has been provided over here as 2R. Basically, R is the radius of the nanorod and 2R is the diameter of the nanorod. So we have considered like nanorods are equally spaced, and that spacing distance is around 2R. So it's the diameter of the nanorod. So we tried to incorporate a empirical relationship with LPD versus 2R. What we can see over here is that when the nanorod length is between 500 nanometer to 1 micron, at that particular length up to 200 nanometer of 2R value, the LPD actually increases with the nanorod spacing, which is a major finding over here. So we tried to find out how the signal and noise actually varied over here in terms of uh, analytical calculation, which we performed using MATLAB simulation. And here we have considered nanorod length from 300 nanometer to 1 micron. This particular nanorod length range we have considered. We get to see that there are some optimum value of R where we can actually get maximum signal and lowest noise, what we can see over here. So it was based on a calculation which we performed using MATLAB simulation, and some analytical calculation has been done as well in this particular work. You can check out my paper on that. And there is this is a clear contradiction with the usual trend, which is increasing signal with decreasing R. It can be attributed to the fact that after the radius decreases beyond a certain value, the rate of decrease in liquid penetration depth is actually more than the rate of increase in surface area. So here we try to incorporate this whole understanding in terms of practical approach, and we have actually grown the zinc oxide nanorods using hydrothermal method on top of electron beam deposition based zinc oxide seed layer. And we try to incorporate PSA molecule and try to see the sensitivity versus concentration value for that. What we can get is that a particular nanorod length, that is 1.2 micron, and a nanorod diameter of around 55 nanometer was actually the optimum length and diameter for getting the maximum sensitivity in this particular case. We have also tried to learn about the specificity of this particular BioFit. In order to learn about the specificity, we need to compare the biosensing device with the similar kind of molecules. Here we have considered CEA, hepatitis B surface antigen, this type of molecules to see the specificity of the sensing device. So the major understanding is that optimum performance does not correspond to the maximum geometrical surface area. And we, by this particular study, we get to see that the optimized dimension for zinc oxide nanorod, which actually resulted in good sensitivity, was around 1 micron length, and radius would be around 55 nanometer. And the detection limit what we can actually achieve with this particular arrangement was 0.02 femtomolar for PSA biomolecule detection. The problem was to modify the zinc oxide height and radius in practical approaches. To tackle this particular problem, we actually modulated the pH and molar strength and deposition time. And buffer, as I already mentioned, like buffer cannot penetrate the whole spacing between two consecutive nanorods. So in order to tackle that particular problem, we have incorporated liquid penetration depth. Now in the next topic, I would like to discuss about vertical electrode configuration for performance enhancement in zinc oxide nanorod FET biosensor. So here what we have done is that we have tried to compare between two electrode configuration. One is uh, lateral electrode configuration and another one is vertical electrode configuration. For the vertical electrode configuration, the electrode like drain electrode has been deposited on top of the zinc oxide nanorods. As we can see from the ACM image that the electrode has been deposited on top of the zinc oxide nanorods. Here we have provided some ACM and optical microscope image for the sensors. Surface functionation is a very great step in order to active the amino group which are present on the surface. In order to do that, first the cyanidation step has been done, and then we have used a cross-linker which is GMBS for modification of the sensing surface. Here we have used COMSOL multiphysics software in order to study the electric field line distribution among lateral and vertical electrode configuration. So what we can actually see is that in case of lateral electrode configuration, all the electric field line actually passes through the seed layer only. But in case of vertical electrode configuration, all the field line was passing not only through the seed layer but also with the nanorod spacing as well. So here two type of resistance model has been considered. In case of lateral electrode configuration, the zinc oxide seed layer resistance and zinc oxide nanorod resistance, they are in parallel. So the equivalent resistance would be dominated by seed layer. However, in case of vertical electrode configuration, the resistance of zinc oxide nanorod and resistance of seed layer, they are in series. So the equivalent resistance would be dominated by zinc oxide nanorods. So when we are providing here, we have tested hepatitis B surface antigen molecule as the target molecule. So when we have modified the surface and attached uh, anti-hepatitis B monoclonal antibodies, which are positively charged, and we have used zinc oxide, which is natural in N type, then the electron would be attracted to the sensing surface. So for this reason, when we actually incorporate the antibody molecules, the current would be higher. And when we actually incorporate the hepatitis B surface antigen molecule, that is the target molecule, which are negatively charged, so the electrons would be repelled and the current would be lesser. That particular phenomena has been depicted for two type of configuration, lateral and vertical electrode. Here we have also studied the sensitivity variation. We get to see that we can actually achieve around 20% sensitivity for 0.02 femtomolar of antigen concentration. So the inference drawn from this particular study is that the sensor to here to tackle the Debye layer problem, we have provided high frequency signal to get rid of that particular problem, and enhanced penetration of the electric field lines through nanorods can be seen over here, and we can actually get 20 attomolar of detection limit from this particular device. Now the problem was here the major problem was to avoid the device screening effect, which has been sought out with the use of high frequency signal, and due to strict memory and runtime limits which is present in the COMSOL multiphysics software, we have considered the spacing between electrodes similar order than with the spacing between nanorods. So in the next work, I'll be discussing on development of electric field mediated electrochemical biosensor based on zinc oxide graphene hybrid nanostructure. So in this particular work, we have considered PET-based substrate, which is a flexible substrate, and we tried to incorporate electric field mediated electrochemical biosensor for directed capture of the biomolecules on the sensing surface. So for this purpose, we have used screen printed electrode, working electrode reference and counter electrode has been realized with the screen printing technique. And here the working electrode has been separated into two halves to provide 19.5 peak to peak voltage for 1 minute between them in order to realize the graphene. Here, graphene has been deposited by a dielectrophoresis method, which is very cost-effective method for graphene realization. And on top of graphene, we have actually developed zinc oxide nanorods. So this is actually graphene ZNO heterostructure, which we have actually realized over here. Now we have also performed some characterization, namely FSM, XRD, and FTIR. So in FTIR, we can see that around 2800 and 2900, there are some peaks. This is due to the CH bond, asymmetric and symmetric stretching of CH bond, which is present in the graphene. And also there are some peaks around 1600 and 3350 centimeter inverse wavelength, which is due to the presence of graphene as well, CC bond and OH bond. Now, if we want to talk about the electrochemical response optimization of the electric field, we get to see that your CV diagram has been represented over here. So in case, as we keep on increasing the antigen molecule, what we can see is that the current level is actually getting decreased. This is due to the fact that as we keep on increasing the antigen molecule, this particular antigen molecule to reach to the sensing surface in that particular liquid environment. So we need something to direct those antigen antibody molecules to the sensing surface, which can overcome the effect of the liquid. So in order to do that, we have tried to incorporate electric field. Here in the right side diagram, we have incorporated 0.8 volt electric field, and we get to see that we can actually distinguish between those diagrams which are present after aptamer, after antigen concentration, which were quite overlapping in case of left diagram. Now we need to optimize the electric field. What we can see is that percentage decrease in peak current is actually getting saturated as we increase the voltage beyond 0.8 volt. So we have considered 0.8 volt as our optimum electric field. Here we have also studied in buffer condition the EIS spectrum for the particular device. This particular CV diagram actually represent the CV characteristics in presence of serum. So what happens is that in serum there are so many non-specific antigen antibody molecules as well as interferent molecules are there. So due to their presence, there is so much noise because the double layer capacitance is actually enhances and the Faraday to capacitive current ratio is actually decreasing. So for this reason there is so much noise generated, so the curve is actually look so somewhat degraded. Here we have considered the percentage decrease in peak current. So what we can see over here is that the lowest concentration, like 1 femtogram per molar per ml, that is actually comparable. The standard deviation of that particular concentration is actually comparable with the blank serum value. So we can't distinguish the blank serum value from this particular lower concentration of antigen. In order to tackle this thing, we know that electrochemical biosensor has got so many components. Three such components is RCT, RAG, and RSOL. RSOL is the solution resistance, RAG is the antigen resistance, RCT is the charge transfer resistance, which is due to the presence of redox current that is there in the electrode electrolyte substance. So if we consider the percentage change in these parameter, then we can actually clearly distinguish between blank serum and the concentration which is present like 1 femtogram per molar. So we can distinguish between these parameters very clearly if we consider the percentage change in those components, that is RCT, RAG, RSOL. So this particular POC device has been integrated with smartphone based devices, and the main inference from this particular device was the detection limit was around 1 femtogram per molar. Here we have used dielectrophoresis method in order to tackle the cost effective way to deposit graphene, and it has been realized on screen printed PET substrate. And we have the main thing what we have incorporated over here is that we have provided electric field to enhance the antigen antibody molecule capture on the sensing device platform. So the problem was graphene deposition in a cost-effective way. So that has been used in dielectrophoresis method, and to apply the differential potential, it is very necessary to redesign the working electrode, where the working electrode has been separated into two halves so that potential difference can be provided over there. So, during my time in UCL, I tried to fabricate quantum sensors. So, this was basically a joint venture between 7 to 8 universities, and the lead research was going on Sheffield University. So, idea of this particular work was to detect action particle. Action particle is kind of imaginary hypothetical particle, which is the primary element for our existence. So we are a bit familiar with the dark matter, dark black hole, this sort of things. So basically, the particle that is actually there in the dark matter is called action particle. So our aim was to detect this particular particle. So idea was that action particle, when comes in close to the strong magnetic field, it actually convert to photons. Now these photons are of very weak signal. So in order to amplify those signals in that particular temperature, very low temperature, we need something as amplifier. So those sort of amplifier has been a topic of research. So I tried to fabricate this quantum sensor, which was based on Josephson junction. So this Josephson junction is basically a kind of amplifier sort of thing. So we can actually consider this as LC amplifier sort of thing. So idea is there are two superconducting materials. We are all know about the superconducting materials. Like when a particular material uh, gets cooled down up to a particular threshold temperature, which is the critical temperature. Below that, it can actually conduct current without any resistance. So, if we join two superconductor with a certain gap, that particular gap has to be in the order of coherence length of the Cooper pair. Now, what is Cooper pair? Cooper pair is basically, in case of semiconductor devices, we are all familiar with electrons which actually conduct. In case of superconductor, there are Cooper pairs, like two electron pairs that actually do all the conduction. So that particular gap between two superconducting material has to be in the length of coherent length of that particular Cooper pair length. So if we make such arrangement, what happens is that each of the superconducting material, they have wave function, and that particular wave function has got phase element as well as amplitude element for that. So when a Cooper pair tries to cross the junction, those wave functions actually interfere with each other, and that particular interference actually gives rise to a current which is called critical current. So in case of Josephson junction, what happened is that up to a certain current value, we don't need any sort of voltage. We can actually directly get the current without any resistance. After that critical current value, the voltage actually gets generated, and this particular voltage actually depends on the flux quantum multiplied by the flux phase difference of that particular Cooper pairs. So this has been realized over here, and here the fabrication technique was we have taken niobium as the superconducting material. So first silicon wafer has been taken. On top of that, silicon oxide dioxide was deposited. On top of that, niobium has been sputtered using sputter deposition technique, and that particular niobium has been patterned. Those junction has been created spacing. So insulator material which is in the junction is SiO2, and the whole structure has been realized using RIE, that is reactive ion etching based technique. And the performance of this particular device is actually still undergoing, like this particular project is still undergoing. I had to drop this project halfway to join Intel. So this is the basic idea of quantum sensor. Now, presently, I am actually working in Intel Corporation, and here I have worked in 18 Armstrong process node, which is going to be, I mean, released soon. And we are all familiar with the four core chips which Intel actually provides, like a Core i7 processor. We all know about that. Particular 18A process node has got two main features. First one is ribbon FET, which is the gate all around FET structure, which is very new over here. And it has got power via, which is like backside power supply, which we have incorporated. So there are several layers when we are actually fabricating our semiconductor devices. So many layers, so back end, front end. And I was actually working on a junction between back end and front end. So I was in contact integration, though my domain has been shifted recently. These are the some same images of the actual transistor. The here, let me show one pointer. Yeah. So these are basically the ribbons, the gate portion, and my job previously was on working on something which was there in here. That is the contact segment, which was strange connect 2, and this particular thing, this is called deep via. So this particular deep via actually connects several interconnect layers, which are stacking on top of one of each other. And this actually connects several links with this particular via structure. And I was associated with one of the one of the contact segment, which was called Range Connect 2. So there are several links over here in the contact portion. Now, I want to talk about two particular process which are absolutely necessary in order to carry out any sort of process in semiconductor fabrication domain. One of such process is called Bosch process. So this is basically like when we move from basic transistor to the 3D transistor and high-end features of the transistor, semiconductor transistors. Main critical thing is to etch, to have high impact etching, high aspect ratio etching. That is like deep via or any sort of etching which actually requires high aspect ratio. So that particular etch has been carried on by this Bosch process. So this is a basically deep reactive ion etching process. So this Bosch process has got two particular steps. First one is passivation step, which is use of C4F8 gas to deposit a protective polymer layer on the side walls as well as the bottom of the layer. And then etching of the silicon actually takes place using SF6 plasma, which actually can etch the silicon, and it actually etches the bottom of the particular device, and it creates further etching without providing any damage to the sidewalls, because sidewalls are already protected by the passivation step. So it's repetition of this particular two steps, like passivation and etching step, actually results in deep um, area, which actually result in deep via or any sort of high aspect ratio etch recipes. Another thing which I would like to discuss about is dual Damascene fabrication process. This is basically a single process which actually can fabricate interconnect as well as deep via. So deep via is actually connecting several interconnect portions. And if we want to fabricate this deep via with the trench, that is the interconnect layer, in a single process, we actually look for this dual Damascene fabrication process. What happens here is that first, a dielectric layer, that is called ILD, interlevel dielectric layer, that has been patterned, deposited, and has been patterned using lithography. After that, there is a barrier layer that is deposited. This particular barrier layer is there. It has got two particular purposes. First one is uh, on top of this barrier layer, there would be metal layer. It can be Cu, copper, or it can be tungsten as well. We don't want those atoms to migrate into the ILD, that is the dielectric level. So in order to I mean protect them from the metal, we have deposited this particular barrier layer, and also this particular barrier layer provides good adhesion to the metal layer. After that, the metal has been first, the seed layer has been deposited using physical vapor deposition. So I have already talked about seed layer in my work as well. Here also in semiconductor industry, prior to deposition of the metal, we first grow the seed layer. After that, electroplating of CU has been carried on, which actually fills the via and the trench portion. And finally, the chemical mechanical polishing tool has been used for polishing the surface, make it smooth. And on top of that, capping layer, which is like edge top layer, which is silicon nitride, has been deposited. So these particular steps keep on repeating as long as we are actually requiring the via plus trench combination for our interconnect fabrication process. In future, I would like to explore some topics. First of all, is I have some plans to explore microfluidic chips in order to simulate organ functions. Especially, I would like to realize vascularization of cancer organoids. I would like to explore that. Let's see what happens. And also, I would like to explore molecularly imprinted polymer-based sensors for viral biomarkers and cancer biomarker detection. Also, I would like to carry out my pending work, which was on quantum sensors in future, I guess. And 2D materials based sensing devices, I also want to explore, especially Maxim based van der Waals devices, which are very crucial in case of biomolecule detection techniques. Also, I have some plans for memory chip based research work, which is on flash memory, 3D NAND, this type of relevant topics which are very crucial these days. So that actually sums up my research experience so far. Thank you, everyone.
Thank you, ma'am, for your presentation.
Thank you so much, sir.
Participants or from your side, if you have any query, you can please share your queries with madam. Madam can share the views on that. Please, if you have any doubt, you can discuss here.
So this quantum sensor and semiconductor device physics based process integration steps, these are very what should I say, like very crucial these days.
Um,
So anyone who is actually interested in this particular domain can get in touch with me, man. We can think together. So yeah.
so related to any question, okay, as there is no queries come from
Mhm.
participants. Thank you, ma'am. Once again, thank you very much for your
Thank you so
presentation.
much, sir. Thank you so much, sir.
Thank you.
Um, I think this is the end, right? So,
This is the end of this session. Yes, ma'am.
okay, sir. Thank you so much, sir, for
Uh,
providing me this opportunity. I'd really like to thank you and Dr. Achar to giving me this opportunity because I'm very new. So I was like, it's very privileged for me to be in such a great audience, so many eminent experts and all. Thank you so much.
Thank you,
Take
ma'am.
care.
Thank you.
Take care.
Thank
Bye.
you. Bye. So, dear participants, our next session will start from 3:30.
Sir, feedback link is there.
Feedback after actually all session will complete and then feedback will be taken.
What time, sir, the exam will start?
Exam will start from 7:30.
In Google link you will send through.
Google form will be shared, ma'am.
Okay, sir. Thanks.
You can share your feedback in Otol link. What is in from your profile? You can share your feedback anytime. You can give your feedback, and examinations will be start at just after the last session. That means session will be completed 7:15, and then uh, examination will be start from 7:30. So these two are very vital, feedback and examinations, because without that certificate issue it will be difficult. So everybody should have to give feedback, and everybody have to participate in the examinations, because all the formalities we have to send, communicate with the Autol link, and after that from the Autol link the certificate will be generated. So these two are very vital.
Sir, after this session only, you will provide the link, no, sir? Feedback link.
Yes, no, actually feedback link is not to be provided here. Feedback will be you can give from your account of Autol FDP account.
Okay, sir. Examination, sir.
Examinations we will share the Google form
Okay.
at
Now,
one place.
okay,
Yes, madam.
after this session over, we will give the feedback.
Okay, okay. Anytime you can give your feedback, no issue.
Now what, sir, we will give it, sir?
Now can we can, I think, no issue.
Okay. Thank you, sir.
Your session 30 minutes is now time is left here. So after 30 minutes, next session will start. That means at 3:30 we will start the next session. Professor Vijay, please mute yourself. Professor Tripathi, Professor Tripathi, please mute yourself. Hello. Professor Tripathi, sir, please mute yourself. Hello, Professor Tripathi, sir. Hello. Please mute yourself.
Red number one,
Hello. Professor Tripathi, please mute yourself.
Red six Deepika. Honor, set, go. Now counter 100 meters start.
सीमांचल सर सिलू सर संपत सर विजय सर उदय सर होगा टाइम है भी करना है क्या रुक ना टाइम आप रेस्ट करो हाँ हाँ उठे उठे बोल जल्दी अभी होगा प्लीज कोई भी भाई वो ତା ପିଛା ହେଡ୍ ପଡିବୁ ବର୍ଷାର ମଜା କେବେ ପାଇନୁ ଆଜି ସେ 5ଟା ବେଳେ ବୃହସ୍ପତିବାର ନା ସୋମବାର ପ୍ରତିଦିନ କାମ କରୁଛୁ
అదెందుకో పెళ్ళి ఉండాలి హాస్టల్ హాస్టల్ పెళ్ళి ఉండాలి పెళ్ళి తీసుకున్నాడు నేను అప్పుడప్పుడు
కాదు సారా ఆయన నాకు ఇచ్చింది చెప్పేది అదే. నేను రోజు తెచ్చామండి వాళ్ళ ఆయన పెంట నా పెంట మొత్తం తెచ్చు మొత్తం ఇంట్లో 3 ఉన్నాయి.
నా ప్రాజెక్ట్ అన్ని అన్ని సిస్టమ్ పెట్టడం కదా నేను ఇప్పటివరకు మళ్ళీ ఇంటి దగ్గర లెఫ్ట్ వాడలేదు
దాన్ని డిసైడ్ చేయడం కరెక్ట్ కాదు.
అందులోనే ఉంది మొత్తం డేటా
పర్లేదు సార్ 8 GB ఎంత తెచ్చుకుంటాను.
Professor Mahesh Kumar has joined with us. Welcome you, sir. Welcome you, sir.
Yeah, thank you. Thank you.
So we are just waiting 1 or 2 minutes such that more participants can join.
Okay, no
Then we
problem.
will start.
Okay, sure, sure.
So let's start. Uh, Professor Mohesh Kumar is professor at IIT Jodhpur. He has received INSA Medal for Young Scientist for the year 2014 by Indian National Science Academy, the AMR SI Medal in 2016 by Materials Research Society of India, and many more fellowship and award he has received from different countries. Recently, INAE awarded him Abdul Kalam Technology Innovation National Fellowship 2022. He is also editorial board member of Nanotechnology IEEE Sensor Journal, etc. He is also fellow of Royal Society of Chemistry and Institute of Physics. He is founding member and serves as chair of Indian National Young Academy of Science. He has published more than 200 research articles in national and international journals. His research interests are focused on 2D materials, nanomaterials, sensors, semiconductor materials, and devices. So welcome you once again, sir, in the FDP in our at NIT Agartala EI department. So
Yeah,
uh,
thank you.
let
Thank you so
let's start.
much.
Yes,
Can
sir.
you see my slides?
Yes, slide is visible, sir. Yes, sir.
Okay, thank you. Thank you so much. Yeah, good afternoon. And today I'm going to talk about the this high electron mobility transistors and how we can use basically these sensors for water quality monitoring. So here we have used this one 2D materials to functionalize the basically the aluminum gallium nitride and gallium nitride high electron mobility transistor, and then finally we have made a sensor. By using this sensor, we can measure the basically heavy metals in the water that currently we don't have in the existing basically our water purifier system is there. In the display, we don't have basically okay what is the quantity of heavy metal ions or TDS is there. Now only we are getting this one. We are replacing the cartridge based on the timing after 1 year or for how much time you are using the filters here. But we need real time monitoring these ions and TDS sensors. So if we can integrate, we can see basically what is the level of these heavy metals are there. That is very important. So as we know this one in our body, almost 60% we have the water, and drinking the pure water, this is essential basically for the human body. And in the different body parts, we have the different concentration of the water. So whatever this one water we are drinking, that should be the clean basically, and should be uh, so if any type of impurity is there, that may be responsible for the disease here. If we see in last few decades, basically water quality has degraded, and this degradation is due to the human. Basically, we throw these steps in the water, basically, or we use for the industry application and then release without water purification. And here water pollution start from the surface water, and what will happen, this surface water again mix with the groundwater and destroy the complete our resources are there. Even in the river, many times we have seen the this Chambal river or another river, basically in that this highly toxic heavy metals are present. Broadly, these water pollutant we can divide in three categories, and here is the pathogenic organisms, organic materials from fertilizer, detergents, and this one we are getting. And third one is this is the heavy metal ions category. These are highly toxic, but few ions, for example, zinc, silver, these are essential for our body in a certain quantity here. Now these heavy metals we are using for the different applications. We use in the agriculture, we use in the industry, in the textile industry we are using lead here. And these basically heavy metals, because now these industries, they don't do the proper treatment and they release the water basically without treatment, and somehow this is mixing with our water resources, and then overall our lakes, basically rivers, these all are contaminated because of these heavy metals here. So if you see in the print media, we are getting regularly these news, basically Yamuna, this water is there, heavy metal toxicity found in the veggies grown in the Yamuna, this one flood plains. Similarly, in the Chambal in the MP, that is also highly toxic. So in the different, basically in regions, we have different rivers, and day by day their water, this quality is there, that is basically degraded, and these heavy metals, basically they are mixing somehow, this one either industry is releasing, or these are coming from agriculture, or whatever other source is there here. So now basically we need some sensors basically to detect how much these heavy metals are present. So at least basically we can monitor our rivers and these lakes water quality, particularly how these heavy metal ions, their concentration is increasing. If you see the groundwater quality, currently we are measuring the groundwater quality, that is based on the TDS, particularly in the this one Rajasthan, Gujarat, here some Maharashtra region, or in Bangalore and Tamil Nadu, TDS level is, this one is very high, that is this red color is the unacceptable is there. But here, how we are measuring the TDS, we are measuring the only conductivity of the water, how much is there. So if TDS is lower than this basically 480 milligram per liter, in that case also, if these heavy metals are present here, then basically water is not drinkable, that is highly basically toxic here. But few here, we call these basically ions are essential for our human body. This one, during the COVID, basically doctors also have suggested zinc here. So these are the limit for the WHO defined limit is there. But for example, lead is there. If this here lead concentration is more than 1 ppb or 5 ppb, that is highly, this one water is highly toxic is there here, particularly if you are using this one here, these heavy metal ions. So how to measure this one, and how to make a online system? So currently what we are doing in the laboratory, we can measure basically by using the ICP-MS is there, one this scientific instrument is there, but that cost is around, we have to spend around 50-60 lakh rupees, and that is not possible, this one, to spend basically this everywhere. Another difficulty is that in these sensors we have to collect the water, and we can do only in the laboratory. If you want to do the online here monitoring, for example, in the river or in the lake, how these concentration is increasing or decreasing, here if you can mount one sensor, that is not possible. So suppose you want to see the temperature of metro cities or pollution, now these sensors basically sensors are integrated with the IoT, your internet, and we can check basically what is the temperature of Delhi is there, how much pollution is there. Similarly here, if we can make some online sensors and we can connect basically here, if you can connect through the internet, then we can collect the data. Okay, this particular river, where is the pollution is there, how pollution is increasing, and in between, if industry is there, basically if they are releasing the water, they are cleaning this one properly, doing the cleaning process or not, all that we can basically we can found here by using these sensors. So how to measure particularly these heavy metal ion sensors? We know particularly nickel, arsenic, here mercury, cadmium, lead, these are the highly toxic, this one highly toxic in the nature. But how to measure? To measure this one, basically we have to see some physical or chemical phenomena. So here there are different basically phenomena. By electrochemical we can do, but this is only possible in the laboratory here, because we need here this special one thing, we need the electrolyte here. Also we need basically these electrodes here, and this is the specific type of this one where we are using mercury sorry, silver and AgCl electrode. So online is not possible. Another here biochemical is there, where we are using basically some nanoparticles and aptamer, and they are making the bond, and then we can find out what is the final product is there. Third one is the colorimetry is there. So if you are mixing some chemicals, if how much color change is there, here you can see in this diagram, based on the color, here is the basically concentration is very high, here is less. So based on the color also we can make. And this here another option is the semiconductor based here. So here we can functionalize our gate area basically, and when these ions are coming here, now the current between source and drain, how that is changing. If we can measure this current and relate with the concentration of heavy metal ions here, we can make by using this concept here. And at IIT Jodhpur, we are trying to make these small devices similar to the glucometer is there. You have seen in the glucometer, just we put basically one blood drop is there. We can get basically what is the sugar level is there here. So similarly here, if we can make this one small sensors here particularly, and now we can dip this one, for example, in the water, or whenever we are traveling this one, we don't know the water we are purchasing from the different basically brands, that is drinkable or not, but we can put one water drop and we can do the testing basically. So here we can use these high electron mobility transistor based transistors, and then we can do the basically these measurements. So now here, to functionalize these materials, we have to use some materials basically. Those materials can absorb these heavy metal ions, and that should be the selective. So here, suppose we are using any material, we have to see basically how interaction is happening between heavy metal ions and the functionalized layer is there. So we have chosen here the 2D materials. In the 2D materials, advantage is there. Here general concept, if we know the confinement makes the mobility low. So if we are doing the confinement here, we know this one in the bulk material mobility is, this one is reducing, and that's why during the COVID we have put the lockdown, so we can reduce the mobility here. Particularly the human mobility here. But when we are going in a nanometer scale where quantum phenomena is coming, so the electronic concept is there, that is totally different. Because of the confinement is there, that makes the basically mobility is high. So when we are doing the confinement here, the mobility is high particularly. So here the example is the, if you take the graphene, mobility is extremely high, this one. If you use the bulk carbon here, mobility is very low here. So particularly the quantum confinement is there, that makes the mobility high. And if any materials mobility is high, that means we can make the faster devices, because device response is depending on the mobility, how much mobility we have. Here you can see this diagram, basically mobility diagram particularly here. So we can consider this is the bulk material is there. So when we are using the bulk material here, you can see basically in that case the scattering is there, that is very high. So in that case, overall the mobility of these electrons or carriers is low. But if you are using the 2D materials here, the mobility is very high. In this case, if we see basically, we have defined the path. In this particular, both side here, potential is very high. And when potential is high, these carriers cannot move particularly in this direction. Now they can move in only the defined path is there. So because of this one here, the mobility is there. This is very high particularly. So here these materials, we can use 2D materials, and we can make the fast sensor as compared to the bulk materials. Another advantage is there. One thing is there that mobility is high. Because of this mobility, what we will get this one, we will get the fast sensors. Another one is there here. Suppose this is my bulk material is there. So in the bulk material, we have the different layers, or you can see this one, we have the different unit cells. So this is the top layer, we have bottom layer, again layer, and below this one is also here. So suppose this ion is not near to the surface, what will happen? These carriers can move from here to here, and when they are moving this one, we can measure here current, either current or resistance we can measure. So electrons easily can move. But suppose we are bringing this ion near to this one, here this ion will try to stop or will try to give the electron. In both cases, what will happen? Now carriers will start moving from this side. When they are moving, suppose this ion is taking the electron, these electrons, they have to basically um, uh, this one take the longer path, and if they are taking the longer path, your resistance will be high. Your resistance will be high. So here basically your this measurable quantity is there, that we are measuring the current current or resistance. Here the change will be this one smaller, but there will be a definitely some change. So initial case, suppose this ion is not near to this one, here carriers can move on the surface. If this ion is present, carriers will take the longer path, and now we will get some deviation here, so we will get some change in the resistance. This is the case of the bulk material. But if we are using the 2D materials, that means we are using single layer or double layer. And now suppose this ion is taking the electron. In this case, what will happen? Our resistance will be very high, or will be very low, this one. So in this case, we can say basically we will get 0 or 1 here. So now the quantity we are measuring here, change will be very high as compared to the bulk materials, because in bulk material we can stop this one current flow on the surface, but carriers can move from the bottom layers. In this case, we don't have the bottom layers here. So in that case here, either there will be a current this one, or there will be a zero current here. So in this case, basically overall the change in the quantity in the resistance or in the current will be maximum as compared to the bulk materials. So this is the second advantage when we are using the 2D materials. Basically our sensors response will be very high. So we can consider this is the field effect transistor is there, and now the channel is forming, your 50 or 100 nanometer is there. That is very this one, here that we can consider as a bulk basically. And because of this one, if you are using the silicon based field effect transistor, in that case we will get the sensing response will be low. But if you are using the 2D materials, so basically what is happening between this gallium nitride and aluminum gallium nitride and gallium nitride, here what is happening, one 2D electron gas is forming. That means here one electron density is very high at the interface, and when very high, we can take the advantage of this 2D electron gas. So here we can make the contact particularly, and then we can make basically these high electron mobility transistors. Is it clear? Or anyone is having any doubt? Basically you can stop me, and in between you can ask me the questions. Am I audible?
Yes, sir. Audible, sir.
Okay. So I request all the audience basically, if they have any questions, they can stop me and ask me the whatever doubt they have. Okay. So between this aluminum gallium nitride and gallium nitride, here this 2D electron gas is forming here. Now how this is forming, basically we can understand here. So this is the conduction band of your gallium nitride, and here is the aluminum gallium nitride. And because of spontaneous polarization and piezo, this one piezo behavior, this aluminum gallium nitride conduction band is not straight. Because of this potential, we get the basically we get the tilt in the your conduction band. Now at the room temperature, we have few electrons here. Now these electrons basically here, because of this tilt, they will stay in the lowest energy state. So here you can see these electrons will come in the lowest energy state of the conduction band. So if you are using aluminum gallium nitride, and gallium nitride heterojunction, these carriers particularly, they come, they particularly come at the lowest energy state. So now these carriers, these electrons particularly cannot move in this direction, cannot move in this direction. This basically movement is not allowed here, because now the energy is very high, here is also high. But in the third direction, if we take the contact, they are free to move in the third direction. They cannot move toward the aluminum gallium nitride, they cannot move toward the gallium nitride, because here the energy is higher as compared to this one. Now they are free to move in the third direction. So in the third direction, we can take the source and drain basically, and then we can make these heavy metal ion sensors. So here you can see now the aluminum gallium nitride and gallium nitride, and now here at the junction basically, because of the piezoelectric and spontaneous polarization, now particularly these carriers electrons are trapped at the interface. When they are trapped basically, here you can see this is the complete Venn diagram is there, and this trapped electron we call two-dimensional basically electron gas is there, 2D electron gas is there, and this behaves similar to the your graphene is there, 2D material basically. So now in the third direction here, we can make the contact source and drain, and now these carriers are free to move at the interface. They cannot move in this direction, cannot move in this direction, but they are free to move at the interface. So at the interface, we can deposit one source, another drain, and then we can make basically these particular, we can make particularly these high electron mobility transistors. Now the tunneling is there through a barrier. We can understand basically how their confinement is happening. So this thickness is there, aluminum gallium nitride. How much we have to take, that is very important. If we are taking very thin, these carriers can tunnel through this one. If we are taking very high, in that case basically we will not get the sensing. So now if we are bringing some, because aluminum gallium nitride band gap is very high, so if you are bringing the positive ions here, electron here, negative ions will be generated at the interface. So we have to play with the thickness, and here we cannot take the very small thickness. Here also we cannot take very high, this one very large thickness, because this is deciding your, this is deciding the 2D electron gas. So suppose here we can understand this is the classical model is there. So as per classical model, if barrier is high, these carriers cannot move, cannot cross if their energy is lower than the barrier. If these electrons energy is, because here energy is lower than the barrier, so these here as per classical mechanics basically these electron cannot jump the barrier. But as per quantum mode basically, if these electrons energy is lower than the band gap, but if thickness of this barrier is very small, these carriers can, here few carriers can basically tunnel or cross the barrier, and this phenomena is called the quantum mechanic phenomena is there. So we can consider these electrons as a wave, and then we can define basically, we can explain using the tunneling phenomena. So we have to play with this one, how much barrier this one, our aluminum gallium nitride layer thick, this one layer thickness should be there, and generally we keep around 20 to 25 nanometer is there. So here you can see based on this one around 20 nanometer we have grown. So we have to grow this material here, because gallium nitride substrates are not available, because when we melt the gallium nitride, before melting your gallium and nitrogen both decomposition starts this one. So here gallium nitride wafers are not available, so we have to grow on a some foreign substrate. Mostly this is grown on the sapphire here, but even we can grow on the silicon substrate, and we do the stress management because of the lattice mismatch and thermal expansion coefficient mismatch here between gallium nitride and silicon. What will happen? Defects will come here, so we minimize these defects, and final our layer is there. Hemmed layer is only these layers. Below these layers we are growing to minimize the defects. Otherwise, if we have defects in the 2D electron gas, they will trap the carriers particularly. So we have to minimize this one by growing, basically by managing this one here, stress management, different aluminum, this concentration we have to take. Then basically we have to grow a thick gallium nitride buffer layer, and on the top we have the this hemmed structure. These samples we have grown by the this one MOCVD, and at IIT Jodhpur we don't have. We have a collaboration with IMRI A Star Singapore. So my students, they grow at this one A Star, do some material characterization. We measure the mobility, and whole mobility is coming basically here around. If you see in the wafer, this is the 8-inch wafer is there, so almost 1800 to 1900 centimeter square per volt per second is there. So, and this is the 2D electron gas concentration is there. So particularly by measuring this one here, we can say this one, our mobility is around 1800 to 1900 is there. And then here at IIT Jodhpur, we process for the fabrication. So what we do this one here, once we get the wafer is grown by the MOCVD, we deposit a tri-metal, aluminum, chrome, gold, and then by the lithography we open a window and we deposit a silicon nitride layer, and at the gate we deposit the nickel and gold here. So particularly this is the high electron mobility transistor is there. We have the source, we have the drain, and here we have the gate. So you can see particularly this is the complete device schematic diagram is there. And once we have grown, basically we have fabricated this one, then we do the testing here. And another, because we are putting inside the water, so our source and drain should not basically should not sort here, because if in the metal also we have some conductivity, sometimes both these are sorted here, so we isolate particularly. And here you can see the device structure. This is the source, here is the drain, and we have the gate. This is the gate particularly, and now the source and drain both we have isolated by depositing this silicon nitride layer. So here we have deposited, you can see this is the silicon nitride layer is there. So this is the silicon nitride layer is there. Next, what we do here at the gate, basically we functionalize this one here with a different materials, and then we make the different this one heavy metal sensors. Because with a one layer we cannot make all heavy metal sensors here, particularly if you want to make for mercury, lead, cadmium, this one we have to use the different functionalizing material, and then only we can make particularly these sensors. So now here what we do in the water, basically we take this one, here is the our device is there, we take the contact this one, and then we apply the constant voltage, and we monitor the current basically between source and drain, how this current is changing here. So we have made first this one, this is one example, but similarly we can make for all heavy metal ions. This is the mercury, and for mercury we have used the this MOS2, again another 2D material is there, and this material is also having the band gap. So we have used MOS2 for mercury ion sensing here. So how we are growing? Generally in my lab we grow the MOS2 by the chemical vapor deposition here. And we grow the different surfaces. This is the very nice vertically aligned flakes are there. But now we have fabricated source, drain, and gate, and here the growth is taking place around at 50 or this 1000 degrees centigrade. So at particularly this high temperature, after the fabrication of source and drain, we cannot grow the heavy metals. So we have used the another this one way to grow these 2D materials. We use the hydrothermal approach is there. So here we use MO3, NaOH and thiourea. We mix basically, and then basically we grow basically we grow these MOS2 here. So here you can see this black powder is there. These are the MOS2 flakes are there. Here this is the MOS2 flakes are there. So these flakes particularly we can use, these flakes we can use basically to functionalize our gate here. So now we have done the X-ray diffraction. In the X-ray diffraction of this powder and by Raman spectroscopy we grow we confirm that grown material is the 2HMOS2 is there. So MOS2 exists in the two phases. One is metallic phase, that is the 1T is there. Another one is the 2S H, this is the semiconducting phase is there. So whatever we have grown by the hydrothermal, this material is having particularly this is having the semiconducting phase. So here next, how is the surface morphology? We have done the electron microscopy, SEM images, and you can see these are the very nice MOS2 flakes. And if you are making any type of the sensors, because here reaction is the surface phenomena is there. If you have more surface, more ions will see it basically. So here these are very nice flakes, and here particularly as compared to the single layer, these flakes can store, this one can absorb more number of heavy metals, and then if you have more number of heavy metals we get the more change in the current. So here we have done these material characterizations. Next, what we have to do, we have dispersed these MOS2 flakes in the IPA, and then on the gate particularly, this is the gate here, we have dispersed by the drop cast on the gate here, or particularly on the gate, and these MOS2 flakes are dispersed on the gate. And next then we have done the measurement. Here you can see the some real devices how we are doing. So particularly this is our source and drain. We have isolated this area by using basically this gel, silicon gel, and then here you can see we have disperse basically this MOS2 on the gate, and finally we are doing the measurement. So after transferring this material also, when we have transferred on the gate region, again we have done the characterization, is MOS2 is successfully transferred, or how is the morphology. So this is after transferring the MOS2. Here is the our hand on the gate basically, these are the flakes. And again in MOS2 basically we got these peaks basically, we have confirmed this transferred because in the synthesize we have used MO2, this one MO3 powder that is completely converted in MOS2 and successfully transferred on the gate. Next, what we have to do, basically we have done the measurement, current voltage measurements. This is the our bare device is there. After decorating with MOS2 here, slight change is there in the current. And next what we do this one, here we have put in the 10 ppm of mercury ions, and then we saw basically our current is changing. So we can apply around 1 volt or 2 volt here. So we can apply a constant voltage, and if we can monitor how current is changing basically, so if we can monitor the current basically, then we can make basically these heavy metal ion sensors. So here is this is the real time monitoring is there. We have applied around 1 volt, and now we have put the different concentration, we have put this sensor in the different concentration of these heavy metals, and even easily, because for mercury 1 ppb is the defined limit is there, so easily we can measure initially this one, because here sulfur ions initially they are having negative charge, so slightly current is increasing, but after this one current started decreasing. So how much decrease is there in the current, that we can measure, and then we can make these sensors. For more detail, you can refer this paper. In the 2020 we have published our first paper, basically how to detect the mercury ions. You can go through this paper. Here is the mechanism, because initially we have some negative this one ions, or this negative charge is basically because of this one. When mercury ions are coming with the positive charge, so because of this one, here there is a increase in the current, and then will start the decreasing particularly. We have done this cross selectivity test. We have mixed all the ions individuals, and we found here MOS2 is only sensing towards the mercury ions. From other ions, the response is there almost is the negligible is there. From mixer, this one we are getting almost same response. So we can say MOS2 is highly sensitive towards the mercury ions, and by using this one we can easily measure. So here exactly what is happening, when these positive ions are coming here, basically your electron density is there, this is changing. So here negative ions are created on the gate, and now here this density, electron density is decreasing. Because of this uh, decrease in electron density, what we are getting, we are getting change in the current. So we have measured the sensitivity here, detection region, and generally we measure this one from 1 ppb to 100 ppb, and from point 1 here, this ppb to 100 ppb, we are getting the linear transfer function. That transfer function is the relation between input and output quantity, and if this here your transfer function is linear, then easily we can optimize at 2 points, and then we can get the basically slope. So in this region is almost linear, but if you are going with the high concentration, now sensor is saturated. So in the lower range, we can measure basically what is the concentration of these heavy metals are there, and by using this one we can make sorry, these heavy metal ion sensors. Another question is that how much quantity of MOS2 we have to load basically on the gate. So we have optimized, we have taken around 10 mg per ml, 20 mg per ml, 40 mg, and we found basically maximum here limit of detection and sensitivity we are getting at 20 mg. After this one is saturating. So basically we have to use around 20 mg here mg per ml, and then we can optimize basically and add particular this quantity of MOS2, we get the highest sensitivity, also we get the low this one limit of detection is there, that also we get the lowest. So we can use this particular concentration of MOS2 flex, and then we can make these sensors. Another, then we have tried to improve the sensitivity and selectivity here. So in the water purifier systems, we use the UV lamp to kill the bacteria in the water if you have this one. So now our sensor, where we have to mount this one. So in the previous case, here we have taken, there is no UV source is there, basically we have done the measurement in the normal light here. But if you bring our sensor near to UV source, here particularly what is happening this one. So when we are bringing near to UV source here, we found this one, our sensor sensitivity is increased this one. So now even we are able to measure in PPT level also, because generally our limit is should be above 5 ppb. So here even 5 ppb there is a large change is there, current is also in milliampere is there. So as compared to the this one, our previous case where we have not used the UV source, by using the UV source we can improve this sensor sensitivity. And sensitivity we got around 548 this one microampere per ppb. And if I compare basically with respect to the previous case, around 850 times we can improve their sensitivity just by putting this sensor near to sensor near to the uv source. So by using this one here, we can improve this sensor sensitivity just by basically bringing or mounting this sensor near to the uv source. So here particularly what we found this one, because uv source is somehow is increasing the 2D materials conductivity, and this conductivity is helping to improve the sensitivity of this material. So what we have done next, basically we have in the amos2 we have grown the mixed type this one. So in the previous case, if you see, we have taken only 2H phase, but here we have taken the mixed of 1T to improve the conductivity of this material. And then we have taken here 2H and 1T both mixed phase. So we have grown this by hydrothermal. Just by varying the parameters, we can grow either this one 2H 1T basically, or pure mix this one. So we have used this mixed phase. And again, one more thing we have used here, that is the gate biasing is there. So by applying the biasing also, we can improve these materials here. We can improve these materials basically sensitivity here. So we have used this here. Now by here Raman spectroscopy, we confirm this material is having the both phases, one T and two phase. And then we have decorated particularly on the gate region, and here also we have applying the gate bias. So in the previous case, what we have done, on the biasing we are not applying. So when ions are coming, now the potential is generated here, build up, and because of this potential, 2D electron gas concentration is changing. But in case some voltage we have applied, and by applying this one here, we can also improve we can improve their response basically, performance as compared to the previous case. So what we have done, if we do the at 1T and 2 phase mixed phase, if you take basically, even our sensing response is very good here. And now around 520 times is higher as 0 volt if you are not applying the bias. If you are applying the bias here at 150 times, we can improve this one. This is similar to the using the uv this one. So particularly these materials here response, we can improve just by improving particularly the uh, just by modifying the functionalizing layer properties, their conductivity. By using the mixing here, we can improve their sensitivity and selectivity. Another here, we thought basically, if conductivity is improving, better to use some external conducting material. So we have used silver nano wires and MOS2, and then we have mixed both. So here you can see we have taken optimized ratio is there. Silver nano wires, we have to take the ratio 1, and MOS2 4, where we are getting the maximum sensing response. And then on the gate, basically this material we have decorated with this particular material. And we found basically here the response is there, this is much higher. Even we are getting in the ppb, in the ppt range here. Our change is there, we are getting, because current is in milliampere, so around 205 times as compared to amos2 we are getting. And here this is highly selective towards the basically mercury ions, and as compared to this one uv, 3 times we can improve these materials sensitivity here by mixing with ag nanoparticle and amos2. Another here we have made, this is for the mercury, and still we are trying to improve this one, these sensors performance, and basically selectivity, sensitivity, stability. here. So still this one we are trying to bring the product in at the commercial level. Next is the lead we have used. So in the near to our Jodhpur, this one district is there, Pali. So there we have the textile industry, and they use lot of this one lead based dyes. And after this one, after the use, just they throw, because we don't have water, this one they throw outside. And in the rain, basically when rain is coming, because mostly in the Rajasthan rivers are dry, this one, so just they throw basically. And when river, this one, in the rainy season we have the seasonal rivers, and this all this lead dye is basically this is going in the, again, the in the water resources and distributing the complete here water cycles. So we have used another 2D material that we call the graphitic nitride is there here. So we have used the graphitic nitride, even we have tried to dope with the sulfur. And then we have made the similar these measurements here. And what we found, this one here also we are able, this graphitic nitride is attracting the lead ions here, and we got the highly selective towards the lead, not the other ions here. We got very good sensitivity, and the limit of detection is in ppd. Generally we need lead limit is around 10 ppb here, so we should easily measure the 10 ppb here. So we have collected from the rivers also this one samples. And initially we have cleaned this one. If some water or something is there, our sensor should not disturb. And then particularly here we have taken this one. So this is the our di water. This here is the, this lake water is there, so change is almost negligible. But in the lake water, when we are adding around 10 ppb, here clearly we can see the change in the current. So we can say here, this whatever this lake is there in the Jodhpur, at least that water is not contaminated with the lead ions, and we can detect particularly these easily by using these sensors. Another one is there, because we are doing at the laboratory scale. Here we can do this one, but how to bring a product, this one. So for this here, with we have the collaboration with University of Edinburgh here through the Royal Society International Exchange Award, and they are making particularly these ICs. They are expert in the basically design part. So now here we are applying around 0.5 volt constant voltage, and particularly when this current is changing here, so we are applying a constant voltage. And now when here also we are applying 1 volt, and if this current is changing, this one we are converting by this IC here pulses we are applying, and we are converting basically, if both here signal is same here, for example 0.5 volt and 0 volt, if this is the same, basically we get particularly same pulses at the same time. So we are converting this one from this delay pulses, and delay is depending on the current, how much current is there. So whenever there is a change in the concentration, particularly there is a delay in the cycles, and this delay we can measure. And then we have from this delay to digital converter is there, and we can get the digital number is there. So we have used our sensors. This is the setup is there, how we have made basically. So here is the our hand sensor is there. We are from here we are applying a constant voltage. This one, this is going in the here in the from the sensor signal is there, and this is the conveyor is there. So we are applying a constant potential to other terminal of the sensor, so that potential difference across the sensor remain constant irrespectively of the concentration. So here we are keeping the constant, and now here we are getting the delay basically in the pulses. Here we have the pulse, but in this oscilloscope we can measure how much delay is there basically when there is a change in the current. So here you can see, this is the our sensors. By using the semiconductor analyzer, we are measuring how our sensors current is changing with the different concentration we have taken. And this is the basically our delay is there in microsecond, how this delay is changing when this current is increasing or decreasing. There is a change particularly, and this is the decimal numbers are there. So now here these decimal numbers we can basically set, and accordingly we can make the complete setup. So from device to this complete basically setup we can make, and then we can monitor basically how particularly how much is the concentration of these heavy metals are there. So now we are trying to fabricate few more. We are trying for arsenic. This one, particularly the western part of the country in the West Bengal and Bangladesh, is affected by the arsenic here. So if you can mount all these on a single chip, and then basically in India, in every house mostly we have the water purifier, and if you can install this one in the display, we can get how much is the mercury, lead, cadmium, and TDS is there, whatever this one, or arsenic is there, we can get in the display, and accordingly basically we can change our filters not based on the time here. So with this one here, I would like to conclude my talk. We have grown this one aluminum nitride and gallium nitride high electron mobility transistors, and we have discussed basically how we can fabricate, how this heavy high electron mobility transistors are different from the your field effect transistors here, and how these are useful this one for the heavy metal ion sensors, because device we are putting in the water, so as compared to the silicon, these are more stable in the temperature, in the harsh environment here. Those are the additional this advantage of using the gallium nitride. Another basically, the device is capable to do the real time monitoring, on site monitoring of the ions, and suppose these industries when they release the water, if government is having this such a type of the sensors, they can monitor basically which industry is releasing particularly these heavy metal ions here, and not doing the proper filtering here. So this approach provides a new dimension of aluminum gallium nitride hem in the field of the sensing applications. So this work is done by my two PhD students. They have graduated, Adarsh and Nipur, and we got these wafers from Dr. Sudhir Ranjan Tripathi. He is the scientist as A Star Singapore, and they grow as per our design. They grow basically for us, and I would like to thank SCRB, because we got the Indo-ASEAN project. Through that basically we are getting these wafers, and we are doing this work. So with this one here, I would like to thanks everyone for joining my talk, and now if you have any doubt basically you can ask me, we can do more discussion part.
Thank you, sir. Thank you. Your nice and informative lectures. Now, participants, if you have any query regarding this lecture, please you can discuss here with the sir. Please raise your queries.
Yeah, you can unmute and you can ask me basically.
Please share your views regarding this lecture. Any query?
Or something is not clear. So I assume everything is clear, or you
Yes.
don't know where in front, or you did not understand
No,
anything.
sir. No, sir.
No,
Not
yeah,
like this.
mostly audience, because we can discuss. We have half an hour time.
Yes,
Sir,
sir.
I
You
have
have.
one query.
Yeah, please.
The sensors that you have developed, so how is it ensured that it is specifically detecting mercury or lead? Because as far as I understood that there are no as such recognition element which were used. So
No,
how
that
is
is
it
the
like creating the specificity?
Yes. So we cannot use one sensor on a one chip. Basically, we have to fabricate the different sensors. So when we are doing, for example, mercury, we have to functionalize with MOS2. So MOS2 basically is having the nature. This sulfur is absorbing the mercury ions basically, because these are the this atom's nature is there. Which atom is attracted toward this one? Which atom this one? So particularly MOS2 is there, that is attracting the mercury ion, not other ions this one. And if you want to make for the lead, in that case we have to use the graphitic nitride. So the functionalizing layer is there, that is playing the role, not the hemp is just converting basically. Okay, from one form to another, this is converting. So how many ions are there? Because they are on the surface, they are collected. So if you are putting, for example, this is the insulator, we can consider. If I am putting the positive charges here, what will happen? In this side, the same negative charge will come. On an insulator, one side if you are putting positive charge, another negative charges will come. So similarly, the 2D electron gas is there, that will change. So mainly the functionalizing material is there, that is deciding this one, which ions are basically is in the water.
Okay, so the MOS2 or the material that is being functionalized between the gate and the, like between the source and the drain, that is what is giving the
Yes.
specificity to that particular heavy metal ion.
Yes. So whenever in the water mercury ions are coming, they are absorbing on the surface.
Okay, okay, thank you, sir.
Yeah.
Any more discussion? Anyone?
Even you can write me this one if you have any doubt basically about the water sensors, or if you have any question on the gas sensor or any type of the sensors, we can discuss particularly, because we are also working on the gas sensors where we are using the machine learning to from the data how to make the selective them, how to stabilize the base line. Also same material we are using for the dosimeters for gamma radiation. So if you have any doubt about any type of the sensors, we are open for discussion. If no, then yeah, thank you.
Yes, if no, then we can conclude that. Uh, Thank you, sir.
Yeah, thank you so
Thank you
much.
very much for your nice presentation, sir.
Yeah, thank you so much.
Thank you.
Yeah, you
So,
can write me this one if anyone is having any
yes,
doubt.
yes,
This
yes.
one. Okay. Okay. Thank you. Thank
Okay,
you.
thank you, sir. Thank you.
Thank you. Yeah. Bye.
So, this session is now closed. Our next session will be start from 6:15. Okay, so everybody are requested to join before 10 minutes so that next session can be starting right time. So now we meet you at 6:15. Thank you. Thank you all.
Hello, sir. Good evening, sir. Sir, am I audible, sir?